Hello! So, in this video we are going to be proving the theorem integration by parts, another of the favorites from calculus. So, in particular, I'm going to state the theorem here, but I want to point out some things that are maybe not obvious. So, we're going to suppose, as usual, we have some functions f and g that go from the closed interval a to b to r. We're supposing these things are differentiable, and as we made a note earlier, just being differentiable isn't enough to claim that the differentiable result, right, the derivative, are Riemann integrable. So on top of saying that they're differentiable, we're also saying that their derivatives are Riemann integrable. So the result then is saying if we have all that stuff, then we have this identity, this equality. So one of the things that is easy to overlook, and this happens a lot at pretty much every level of math, including research at times, it's easy to overlook the fact that there's a very subtle underlying thing being claimed here, which is that not only is this equality true, but that each of these pieces makes sense. Because if you notice here, we're claiming that f prime and g prime are Riemann integrable, but I have f times g prime, and I haven't asserted anything about their integrability, whether it's Riemann integrable or not. So I'm asserting that not only does this thing equal all of that, but that this thing as a term has a value. It makes sense. I can actually do that integral, okay? So the first thing I'm going to do then in my proof, so first, we prove our assertion. I will put in parentheses makes sense. Which is to say, i.e. in more rigorous terms, that each term is defined, or properly defined, right? That this thing actually does have a value, and thus I can talk about what it's equal to, okay? All right, so since f and g are continuous, since they're differentiable, they are continuous, sorry, skipped ahead. Since they are differentiable, I'm going to abbreviate, they are continuous. And hence, f and g are themselves Riemann integrable. Okay, so I have that f prime and g prime are Riemann integrable. I have f and g themselves are Riemann integrable. Moreover, we've shown that products, sums, and differences, I guess I should spell that a little more, differences, so doesn't look like differentiable, of Riemann integrable, which I'll abbreviate as Ri, functions, are also Riemann integrable, right? So we now have that f prime and g prime, f and g are all Riemann integrable, and we've shown in the past that product sums and differences of Riemann integrable things are themselves Riemann integrable. So, in particular, I have that f times g prime, right, the product of the Riemann integrable f and the Riemann integrable g prime, as well as the f prime and g, and for reasons that aren't obvious yet but will be very soon, the sum of these two, fg prime plus f prime g, that all of these things are also Riemann integrable on AB. Okay? So these two are there because that gives me this piece and this piece, and now I know this thing makes sense, because obviously I can take a product of f and g and that's fine, right? I don't really even need to know anything about them to be able to take their product and claim that that is well defined. So I'll also say, let's say also, since f prime, since f, let me write that correctly, since fg, the function prime, the derivative of f times g, is f prime g plus g prime f. I guess I should have written that in the correct order, but whatever. Right, this thing is Riemann integrable, so in particular, f times g quantity prime is Riemann integrable. And I didn't write this, but it should be clear that if f and g, they are each differentiable, then we know their product is differentiable. So this thing makes sense, and because that is that, and that is Riemann integrable, this thing is Riemann integrable, okay? So all of this is basically saying all the stuff I am writing and all the stuff I'm about to write, all of this stuff is well defined, makes sense. I can do it without sort of having done some magic behind the scenes thing that made everything blow up, right? Okay. So I'm going to return to this idea here. So I have f times g prime. F times g is differentiable because f and g are differentiable. And f times g prime is this thing, is Riemann integrable. So by the fundamental theorem of calculus, which we've done a video on, I know that the integral from a to b of fg quantity prime on x dx, this is some function prime. So by ftc, I can take that function because it's Riemann integrable, pull it out, and I get fg applied to b minus fg applied to a, right? So by the fundamental theorem from calculus, I have this equality because that fits all of my criteria to use the fundamental theorem of calculus. Or you can think of fg as being itself a function, like h prime, then there'd be h of b, h of a, right? But on the other hand, I know that f prime of g, fg quantity prime, is this whole mess, where each of these individual pieces, as pointed out, is Riemann integrable, right? So I could write this piece just on its own merit, not by fundamental theorem of calculus. I can write this piece as being equal. So maybe I'll write this as star. So star equals the integral a to b. And I'm just going to go ahead and split this over the sum piece here. So this is going to be f prime g applied to x dx plus integral ab of fg prime applied to x dx. Right? So I have this thing equals that equals that. But now I'm basically where I want to be, right? So my goal was to show that I could do some fg prime equals this minus that minus that. So if I just take, I guess, this piece and subtract it over, I'm going to have this thing. So I'm going to have the integral a to b of fg prime applied to x dx. This piece equals, subtracting that off of here, I'm going to get product fg applied to b minus the product fg applied to a minus this integral, right? So a to b of f prime g applied to x dx. And that's exactly what I wanted, right? So this is the integration by parts formula. If you remember how it was shown in the actual calculus class back in the day, it's very similar. The only difference here is that I have to go through this effort of making sure that things are actually well defined before I do exactly the thing that you did in the sort of earlier calculus version, right? Calc 1, Calc 2, Calc 3, depending on where you took it and what you were doing in that class. All right, so that's it.